still try to keep it open if someone from the live stream people wants to ask a question. So I'm still trying to answer questions on Slido if they come, if someone's joining in from remote. For the very unrepresentative survey, have you seen this exhaustive tabulation for Russian trick somewhere? I'll comment more on this name. Tamio mentioned that he knows it under this other name for Russian technique. This was what I just briefly sketched in the original context where it was proposed for Boolean matrix multiplication. Okay, so then let me start and maybe recap a bit. The context is still pairwise alignments, and for all that follows, you can essentially assume we're just looking at edit distance. There'll be a few more comments about improving other things. I mean, what we've just seen in this previous chapter was the idea of having an alignment where we only care about the exact alignment or the exact edit distance. If it is below a threshold, then you can avoid filling in some parts of the matrix, depending how big K is most of the matrix. And so you may be closer to linear time again. But it only works for sequences that are very similar. These are also called banded alignments for, I guess here, the obvious visual reason. Apart from those, you could ask yourself the question, is this inherent that we need quadratic time if the strings are both length n? It's n squared time for the dynamic programming. Is there something inherently hard about this problem that makes it take quadratic time, as opposed to, you know, some better running time, quasi-linear, n log n, something like that? And I'll come back to this lower bound question. It's certainly not true that n squared strictly is the best we can do in terms of upper bounds. That's the context or the content of the outcome of this technique, exhaustive tabulation. I illustrated it last time sketching the application on Boolean matrix multiplication. I typed up the details in more clean ways so that we can work out what this illegible power of the log here in the denominator is. But the gist at the end will be that we bring down the number of operations to something slightly below the standard straightforward algorithm. So cubic time for matrix multiplication and quadratic time for the alignments. Let me also point out here, when we say Boolean matrix multiplication, you actually have to say what you mean by that. What are the operations, multiplication and addition? If the input is a 0, 1 matrix, you may still have in the output numbers up to n, right? You could sum up to n entries, all of at most of value 1. Usually when people talk about Boolean matrix multiplication, what they mean is that multiplication is and addition is or. So it's in the Boolean semi-ring. You could also replace operations with different types of operations that have the properties of a ring or a semi-ring, but may not have a minus in that sense. For example, a popular one would be to replace multiplication with addition and addition with maximum or minimum, min plus matrix multiplication. And that is essentially all pairs shortest paths in a graph. And for that, indeed, the kind of speed up from exhaustive tabulation is the best we know. The kind of tricks of fast matrix multiplication don't even apply. So in some sense, this exhaustive tabulation is more general than just matrix multiplication in the classic sense. That's what I wanted to mention here before from last time. Let me comment on the name of this technique. I've abandoned the for Russians technique as a name because it's a terrible othering term. It was, I mean, there's an original paper in Russian by these four authors, Aglatsarov, Dinitz, Kronrod, and Parachev, probably butchering the pronunciation. They all worked in Moscow in different institutions at the time, so clearly they were all Soviet nationality at the time. Kronrod never lived to see the what we today call Russia again, so who knows if it's appropriate to call him Russian. Haha. Dinitz emigrated to Israel and now has Israeli citizenship, as far as I know. So it's at least borderline today. And I mean, it's just not a great term. It very much sounds like Iron Curtain. It's in widespread use, so you should know what is meant by the name, but I will use something that's much more telling because exhaustive tabulation is what this really is about. And we could do it the same kind of disfavor in forgetting who invented it as we do for other computer sciencey techniques. Where the advantage is that we give it a name that tells us what it is, not who might have invented it. The joke in math is things are always named by someone who invented it the second time or so. So even giving credit is nice, but giving credit inappropriately or incorrectly is maybe less nice than just calling it by some name that reflects the content. Anyways, so here in kind of a bit more cleaner write-up, the same application, which is, I should say, is not exactly what they initially thought about. It's not the way they framed the technique. Indeed, they get a slightly better speed up at the time, but the way I'm presenting it here generalizes to other problems. So I think this is closer to the essence of what we now today see as the exhaustive tabulation technique, even though it's not historically how they first thought about it. I don't know, maybe in hindsight, you appreciate this more. I can maybe sketch at the end what they originally did. I want to also use this name here because we'll reuse that, where, again, think of multiplying matrices. That they're Boolean is not even so important. They could also have values from another very small universe. The point is it has to be a small discrete universe, not some unbounded or even real numbers, something like this has to be small discrete. And there's some way to define what multiplication and addition do, and we're not very fuzzy about the details of what these operations are. In particular, you can do it for min plus multiplication as well as for the more standard Boolean multiplication. Okay, long story short, you divide all the matrices into L by L square sub-micro matrices. Then clearly all the matrices consist of that many micro matrices, n over L squared. And each entry in the result you get from summing up n over L little products. That's what we had last time as well. The number of possible different pairs of micro matrices really is this number. Right? You have 2 entries for each of the L squared cells in the micro matrix, and you have 2 of these, so you take the product. That feels like a lot, but it's not a lot if L is sufficiently small. That'll be the point. In particular, if you use square root log n with an appropriate factor, one quarter is enough, then you get precisely the square root n different combinations of pairs of micro matrices. And since that is not so much compared to the input size, you can afford to compute all of those that could possibly arrive, whether or not they occur in your matrix. And we can do this for whatever operation is convenient. Here, we really don't care, and we'll just have separate tables for multiplication and for addition. Right? It's completely oblivious to this definition of the matrix multiplication. Then if you look at so how we arrange this table of results, also you have flexibility, but one option is you just list all the entries of the 2 matrices, one after the other, and you treat the entire bit string of all the entries as one giant, or maybe not so giant, binary number. And because it's a number, you can use it as an index in an array. And so with a single memory access, you can read off the result of these micromatrix operations after the pre-computation. And the pre-processing, you can also work out, like depending how expensive the pre-processing is. Maybe it's at most cubic, and then the size of the L cubed works out to log to the 3/2, and you have so many of these. Okay. Now the total time to compute one entry in the result is summing up n over L of these micromatrix products, right? You could do the summing up in constant time each because we pre-computed the sums as well, just because we could. And so the total time is n over L for each output cell. N over L squared output cells makes n over L cubed in total. And so you get this, the total time n cubed divided log to the 3/2. And the original variant of the 4 Russian authors, or not of Soviet authors, they divided the two matrices into very thin or wide very thin or tall strips instead of little squares. And then you can work out that there's you're essentially decomposing the result matrix into a sum of low rank matrices, and you can compute all possible low rank matrices the way you need them in an efficient way. So you're using the same trick, that there's only a certain number of possible ways that you have to compute these, and you can just brute force those. That has the benefit, you only have one L in this formula, so you can make L substantially bigger, square of what we had, and so you get a slightly better speed up in the end. They can't do the summing, they have to do trivially, so they don't get the third power of L here, but they have a larger L, and so here this works out as the better result. The way I present it here is not to convince you how to do matrix multiplication, but to teach the technique that will apply to our string alignments. And there it's a bit easier if you work with these squares. How can we apply this to edit distance? We have as output a matrix, so clearly there's some superficial similarity, and we can divide the output matrix, our L, in some submatrices, micromatrices, L times L. The way the alignment matrix, or the dynamic programming matrix, is set up, these correspond to two substrings of the strings that we align. And now you have to study a bit deeper what the problem is about. And here I took the figure from Dan Gusfield's book, where this is also explained in more detail than I'll talk about if you want to read it up. There's different parts in the matrix. There's the top left corner, which plays a somewhat special role. Then there's this first row and first column. And of course, there's the string, the substring that corresponds to this cell. And the claim is that you can compute all the values in F, which, if L is not very tiny, here L is 4, so it's a small example. But if L is a little bit bigger than that, F is the majority of the matrix. It's the big part of the matrix. And you can compute all the values in F just from these A, B, C, D, E. Why is that useful? Well, we can, again, apply exhaustive tabulation to all those entries. A, B, C, these are not too many numbers, roughly L numbers, 2 L numbers. And then there's some letters from the strings. If we make L sufficiently small, there shouldn't be too many possibilities how these can look like. And so you could pre-compute filling much of the matrix in the same way we've done this for Boolean matrix multiplication. There's a few catches, though, in that if you think about the typical edit distance matrix, it tends to start with zeros, and then the numbers progressively become bigger. And at the end, in the bottom right corner, you have the final edit distance of the strings, which might be up to n, right? We hope that it's a bit smaller, otherwise the alignment is useless, but it might be large numbers. it's certainly not just 0 or 1s. It's certainly not just a bounded range. It grows with the input size. In anyways, in the worst case, it does. So this doesn't seem to work. How can we apply this exhaustive tabulation here? And the trick is the numbers do grow, but in a way, they grow in a very predictable fashion, and they can't grow by all that much. They don't jump. You usually do an increment by 1, maybe you leave something the same, but that's about it. So in a way, we want to use a difference encoding, and then things are back to a nicer small range. In the recursion, you never decrement a value, but you do the minimum from different places. So if you carefully study this, if you look at a certain cell and its neighbors, so here's ij, then you might go to the next row or column, and also the diagonal one. So these are the differences that we look at. Each of these cells takes that upper left one as one of its minimum possibilities, as one of its entries in the minimum of 3. And so clearly these cells will not be much bigger than the top left cell. That's the trivial part. The difference cannot be more than 1, but it can also be -1 in cases where the minimum comes from the outside of this little figure. So if this cell takes its minimum from above or from here, then you can work out that it might end up being 1 smaller than the left neighbor. Basically, if you have some value x here, what's the worst it can happen? This can be the same for edit distance. This could be x plus 1, right? Then you have your distance 1. That's one case, and you have to study the others. In principle, it could go up and down, could go up for a long time, and then at some point you branch off. But you can show you never differ by more than this plus minus 1. So if you apply conceptually the operation to the differences, not the matrix entries in absolute terms, then we can still use this exhaustive tabulation. One way to do it that is, again, optimizing a few things a little bit further is that you leave out this top leftmost cell, essentially give that an offset of 0. And now each of the cells here, these are input cells that you have to specify. Same with this. Let me maybe mark this. These are cells that are input to the micro operation. And these are outputs for the micro operation. Each of these cells you have to read as a difference to the left neighbor. Right? This cell could be substantially bigger than the left top corner. But if you want to know its value, you have to add 1, subtract 1, do nothing, add 1. So it's 1 bigger in this case. Okay. These you fill essentially from the recurrence that comes recursively back to you. And now the micro operation has to fill the light green part. And that is all determined from the numbers that you have. And maybe the string as well. Although you can also, like in this more recent paper, they tried to get the dependence on the string minimal. The number of different micro matrices, if you include the string in the simple version, is 2 strings of length L each. So if you have sigma characters, that's sigma to the 2L different possibilities of things that you could have written on top of the matrix. And the entries in the top and left first row, first column, they can be one of 3 things each, plus 1, 1, minus 1, plus 1, 0, minus 1, and we have 2L minus 1 of those. So here, if we want, again, the number of different micro matrices that we have to do the exhaustive tabulation for to be reasonably small, say root n, we have to pick a fairly small L. In particular, the log here is involving the alphabet size. So even if we set sigma to 4, that's already taking log base 12. So if you think about it, that's essentially the length of a decimal number, right? So you want to be in the millions before this makes any sense. So in practical speedup terms, you have to work on this more, and people have tried to reduce the size here a bit more. But in theory, like if you look just at the asymptotic scale up and pretend that sigma is a small constant, it helps a bit. So in particular, you can choose L to be essentially a logarithmic. You have n over L squared micromatrices to fill. By the way, in each case, you're never filling these middle values in the recursion, at least not until you have to. And you can work your way around to never do it. Filling the table this way gives you the bottom right corner, which is the answer, the final edit distance. And for the backtrace, you can also involve micro matrix operations if you want to. Okay. The only thing you fill is this grid of this sparse grid of rows and columns, which gives you enough information for the next cell to feed into. So overall time under these assumptions are improved a good bit. You essentially get the two logarithmic factors speed up. One from filling fewer numbers. The number of things you fill in the cell goes down by this logarithmic factor. And you're also speeding up the computation in the micromatrices by doing table lookup. It becomes constant time, what used to be size or linear in the size of the submatrix. Okay, so that's the positive part. Now, I said I started this section asking, can we do better? Is there something inherently quadratic about edit distance? And it seems so. This is all fairly recent developments compared to other parts of complexity theory. This is from an area called conditional lower bounds or fine-grained complexity theory, where you try to use NP-hardness-like reductions to prove lower bounds for polynomial time algorithms. And in this case, the result you can prove is that any edit distance algorithm for two strings of length n that would take a strictly, so for, well, n to the 2 minus delta time, but delta has to be a constant. So our logarithmic scalar speedup does not qualify for this. If you had such an algorithm, you would refute the strong exponential time hypothesis, which is listed down below. I'll briefly comment on it. But for this module, I guess you can pretend it's a somewhat widely believed complexity theoretic assumption. So we don't have strong evidence in either direction if you're very strict, but a lot of people are building things on top of Seth, the strong exponential time hypothesis. And nobody has refuted it. So it seems reasonable to assume that this stronger running time for edit distance is not possible. So people often call this strictly subquadratic or, sorry, was there a better term? Truly subquadratic, something like this. It's not very well defined, but what we mean is the exponent should be strictly less than 2. The exponential time hypothesis is something that popped up in advanced algorithms, where it says I can essentially not solve 3-sat in sub-exponential time, but I might be able to squeeze the exponent or the basis of the exponent to some smaller constant than 2. Who knows? You should compare this to the easy brute force algorithm for 3-sat, where you just guess an assignment, and that there are 2 to the n assignments or 2 to the k for the number of variables. So that's easily doable. The exponential time hypothesis says maybe you can lower the exponential growth by some constant factor, but you need exponential. And this is, I think, very widely believed. It's stronger than assuming p not equals np, but still there's good support for this in terms of the number of people that speak up for it, whatever that says. The strong exponential time hypothesis makes this assumption a bit more quantitative and a bit more strict, or a bit more strong, hence the name. Here you look at the generalization of 3-sat, where the literals have k literals. Sorry, the clauses have k literals each, not just 3 as in 3-sat. And then it says, whenever you pick some epsilon by which you want to improve the exponential basis, then there is a size for the literals where you'll fail, where the k-sat problem needs at least, well, the stated bound. You can't reduce the exponential basis arbitrarily much if you're willing to look into larger and larger clauses. And so that's the thing that this statement here is based on. Again, all the algorithms we know respect this, so we have no reason to believe it's false. So in a way, we have a lower bound that says we can't reduce the exponent strictly by anything that is constant. And we have an upper bound that says, yeah, we can shave off logarithmic factors. And for a whole class of problems, that's the kind of state of the art. Okay, so edit distance is one of these. Unlikely that we'll see subquadratic algorithms in the strict sense. That's maybe worth mentioning that this reduction even works if the alphabet is constant. So it falls in this range where we do get this logarithmic speed up from the exhaustive tabulation technique. Okay, one more thing that we can do to our pairwise alignments is at least save a bit on the space. So I've said probably quadratic time we'll have to live with unless you count these logarithmic improvements. But maybe we can at least improve the space, which is also quadratic if you do the dynamic programming in the cookie cutter template way. It's actually very easy if you just care about the final edit distance as a number, because the next, well, you can do it many ways, but you could say the next row that you compute, it depends only on the previous row. So you store these 2 rows, that's the very maximum you need. And you can, that's clearly enough to compute the final value. So that's bringing the space down to linear. And you can actually do it with a single line if you remember that you also have the dependencies in an orderly way. So you would only depend on this prefix of the previous table, and then the more you move on, the more you can delete. So you depend on the suffix of the previous table. And so you can keep writing the new table here and keep the entries from the previous row in the rest of the array. It's a bit confusing, but it's actually not hard to do. So if you care for the details, they're spelled out here. We have a single row, and depending which index we're currently in at the iteration, the entry is the current row or the previous row. You have to be a bit clever with keeping the entries, the match entry, which is the one that you're currently overwriting. So you have to keep it from the previous one in a local variable. But my point is, conceptually, the 2 lines would have been fine, and that is trivial to do. Right? There's just no point of keeping the 2 rows ago in memory if you only care about the final edit distance, the bottom right entry. Now, if we want to do the backtrace, that's not true, right? The standard backtrace needs the entire table, because at each point it asks, oh, where did the minimum come from in the bottom right corner? Fine, I'm going to go diagonally up. Then I'm going to go there and ask, where did the minimum come from? But to do this check efficiently, I have to know the 3 things that I'm comparing. So there I need the quadratic space, it seems. Anyways, that's true if you use the standard backtracing algorithm as it pops out of the general template. But you can do better here. In a way, it's again, because this dynamic programming problem is so nice and structured and everything, the dependencies are all very local. And the idea is a cool chimera of divide and conquer and dynamic programming. You kind of use the two mixed together. We use dynamic programming to reconstruct the edit script, but we use divide and conquer to reconstruct the edit script, and we use dynamic programming to help us decide how to break things up. So I can try to cut A in half. So I'm going to have my table. Here's A, and there's B. I'm trying to find the optimal path from top left to bottom right, which is some walk here down, something of that sort. It will have to, at some point, cross the middle of A, clearly. So if only I knew this point, I could independently reconstruct the top part and the bottom part. And I can even say this is restricted now to this part of the table, and this is restricted to this part of the table. I might actually never need to look into this ever again. Now, we don't actually know this point in the middle, right? All we've done so far is compute, say, the score in the last row. But we could make that our next target, and we can use dynamic programming for that. This is a standard dynamic programming task. We can separate the problem into several parts, but there's one breaking up point where we have to guess, because we don't know upfront a priori which breaking point in B we have to use. So we use dynamic programming to compute that one. How to do that? Also, are we now not getting back into the same problem that we need quadratic space to find this middle point? And it turns out no, because finding the middle point you can do with the scores or the edit distances, not the backtrace result. If you want to do it in just the way we've done it so far, then you would need the backtrace, but you can work around in a different way. The best breakpoint in this picture, maybe let me take that. Such a lovely drawing. The best place to make this cut, and this is our J star. It's going to be the best way to go from the top left corner to some point here, and then the best way to continue from there. And these two are summed up. That's the total edit distance. So I have to find the J star that makes that sum minimal. I can do that if I have the entries from here to here, so the edit distance matrix row in the middle. If I have that row, I get all the optimal edit distances from the start on the best path from top left corner to this point. That's what my score already computed. Now for the second part, this doesn't seem to work because we get all possible start points, but the end point is fixed, right? But we can just use the same computation, but reverse the string, reverse A and B. Then what used to be the top left what used to be the bottom right becomes the top left. And we do the same kind of calculation. Edit distance is symmetric anyways. It's the same whether you reverse both strings or not. So there's nothing lost. You could have also written separate code that works backwards. But in the interest of reusing code, I think it's more elegant to write it with the reversed strings. And so that's the final code. There's some boundary conditions, what you do if the first string is very short, and you need that for the recursive call at some point. And this is computing the edit script. So in the notation we've used last time, if the first string is empty, all I can do to produce from the first to second string is inserting all the characters. Likewise, if the second string is empty, I'm deleting all the first characters. If this first string has a single letter, then it's already non-trivial. I have to find the best place to align that character with. So I'm finding the position in B that best matches A according to my alignment score. For edit distance, it would just check if there's an occurrence of the same letter. And then the edit script is getting rid of the first part of B, then replacing the one we found, replacing from A to that letter, and then inserting the rest of B. The interesting bit is if A has some more than 2 letters, then we can do a recursive call, splitting A in the middle. The scores for the top part we compute with just the standard dividing dynamic programming algorithm we've seen so far. For the bottom part, I'm reversing both strings. And then you have to also keep in mind to reverse the indices. So this is a bit of, you want to draw the picture and do it. But conceptually, it's the same thing as the top part. And so by just adding those up and finding the best split point, we get our middle point. This point I star j star is then the midpoint. So the edit script we get from this is the best edit script to get from 0, 0 to I star j star, plus the best edit script to get from I star j star to mn. Again, really think of it visually in this graph of points. So you have the 0, 0 up here and the mn down there. There's somehow in the middle, there's your I star, j star. And then it's the best path from here to here and the best path from here to here. Okay. How long does this take? The non-recursive cost, what we do down here, I mean, here we have some linear costs that's dominated by the rest. The main cost comes from these calls to computing rows because they have to fill the entire matrix. They forget most of it straight away, but they still have to compute all the rows one after the other. So these two together have theta nm cost. That's for the computation, but the space remains linear in n, sorry, it's rows. So in all of this, I'm assuming that m is the bigger of the 2 strings. You can flip that if not. So we get the better of the 2, the smaller of the 2 strings as the space complexity. So this is the part we have to compute in the non-recursive cost. But then I'm also recursing. Now each time I'm making the first string a half as long. So I can have at most log m recursive calls. So a very conservative estimate would be log m times nm, right? That's an n times m. But actually, if you look a bit closer, it's better than that because we get rid of half of the matrix in every recursive call. That's because, again, my picture, if that's your optimal midpoint, the recursive calls only look at this part, and that's precisely half the matrix. So by the standard geometric series, you sum up the full thing, then half the thing, then a quarter of the thing for the recursive calls in total. So the next one, right, will split somewhere here. So again, you're zooming in on a smaller and smaller part. And so the total size of all these parts sums to nm. So the total cost is really nm, which is the same in terms of asymptotic theta class as we had for the more space inefficient version. But we, at all points in time, only just need a single row, or two rows of the matrix. Let's say, let's not get too Catholic about this part. Constant number of rows. Cool, eh? That's all on pairwise alignments, and maybe a good point for a short break. Yeah, which one?
The nice one.
I don't think there was one.
I'm joking, like this is the one like
The one I called nice, this one?
No, well, it's fine still. Any of them like
Okay, now in this part.
yeah.
Okay.
The second part
Yeah.
depends on the first part.
It only depends on the first part via this point. So I guess the easiest way to see it is maybe from this line of the sums of scores. If you think about the backtrace, you know, forget about space efficiency, compute the entire matrix. What does the backtrace algorithm do? Well, I mean, we can, at the expense of clicking a few million times, we can go back. Okay. Here's the backtrace, right? At each point, it goes from the current position, and we start at one precise position. You should think of ij as the current location in the matrix. And then, depending on the values, we either go a step up, or a step left, or a step up left, diagonal. That's the only thing that can happen. So the backtrace will describe a path back through the matrix. Now, if I tell you up front, I'm somehow by magic insight, and of course the magic insight is a calculation with dynamic programming, that you'll cross the middle line at this point, then conditional on that being true, it doesn't matter what you've done to reach that point to go on from there. And kind of by the same, like if you know you're going to hit that point, how you continue after that doesn't matter. And that even was true before then, right? The next step in the backtrace didn't at all depend on the previous path, apart from the point where you ended. Yeah, it's a bit, it's an algorithm you need to wrap your head around. You can either do a concrete example and just work it through. I don't have the book with me, but there's some worked examples in this book. Now I could actually check if I can find it in the online version. Let's see. That's this Compo Pevzner. They discuss this in, like I say, a bit more pedagogical detail. Okay. I might have misremembered in that they had a specific example that I was looking for. You could say like, okay, sorry, I misremembered. I thought they had a concrete example where they show this. They argue a bit more that you can do the reversing of the strings and so on.
I think I looked at it too simply because usually when you look at it from left side, like a point from like that area seems like closer. I mean, I know there are like numbers here, like the
Yep.
effect, but visually it looks like that. That's why they eat up point.
So I think they do they flip the two dimensions, right? Whatever I said with we take the middle row, they take the middle column. For some reason, that's why the divider here is the middle. But that's not what you meant, right? Yeah, they argue about the running time. They have an optimization here where they say instead of looking at the middle point, you could actually look at guess the middle step. What brings you from the middle column to the next one? And that shaves off a tiny bit more of the matrix in the recursion, which asymptotically is not a big deal, but for small enough, I mean, it might make a measurable difference if you implement it. I'm happy to believe that.
A friend of mine told me just now that none of the 4 Russians are likely to.
Well, ethnic Russians, like, is even what's a Russian? Yeah. I mean, at the very least, our American friends of the time should have said Soviets, right? If anything.
Well, at that time, I don't think distinguished between Soviets and Russians.
That's part of the criticism.
Americans now don't even distinguish between Soviets and former Soviets and not former Soviets.
I know. And I mean, this one goes further. They essentially don't distinguish between the 4 Soviets, right? They don't care what they were called. That's the point that's really like not nice. So yeah, exhaustive tabulation. It's a good name. I'm on a mission to convince the rest of the community to use it too.
You can actually say this property as a function, the DB function being Lipschitz continuous.
Are you in a sort of rabbit hole on Lipschitz dependencies, Lipschitz function? Okay, I think we've beaten this problem to death in terms of pairwise alignments anyways. After we've seen lots of different variants of pairwise alignments and ways to solve them, small polylog speedups, space-efficient speedups, etc. At least the conclusion in all these cases was we have reasonably efficient algorithms for solving all variants of these problems. Now, the biologically more relevant version of the problem is not taking 2 sequences, but taking many sequences. That's called multiple sequence alignment, MSA. And just to briefly motivate again where this comes from in the biological context, one benefit or one strength of pairwise alignments is actually a problem in the applications that we use it for, in that sometimes if you just take 2 sequences, they will have some similar regions just because of random chance. And then we would identify these as, oh, these are highly conserved, these must be important, etc., when it is just a statistical fluke. And this becomes much less likely if you don't use just 2 sequences. That's a kind of obvious observation. If something's just shared between 2 sequences, like one sequence you fix, the other is random, so you just have to match one random thing. If this happens simultaneously for many sequences, is much less likely to occur in at least our completely random null model. So it has more significance. And some bioinformatician put this in much more metaphorical language. Here's an example from hemoglobin again that we've seen at the very beginning of this chapter, remember there's two types of globin protein molecules that make up, so 2 copies of the alpha, 2 copies of the beta make one hemoglobin molecule in humans, in healthy humans, I guess. If you look at this one version of these in different species, so there's us, but there's also mice and chicken and zebrafish and this African clawed frog as some example of species. I mean, these are all animals, but they're not super close, right? They're not all mammals, etc. Still, you can build a multiple sequence alignment of the beta globin in all these species. They all need to transport oxygen. Even insects have hemoglobin, it seems. So this is a very widely shared function. And indeed, all these proteins can be aligned with reasonable agreement. So the star means exactly equal. No, it's not true. Is that? It's a bit hard to see because I had to scale it down. I think the star should mean equal on all columns. It's just here. This is the L, not the A. So star means exactly the same in all 5 rows. And colon and dot are varying degrees of still chemically similar. So the colon still means chemically similar. I think the dot is essentially a mismatch. And then there's also spaces for even worse mismatches or gaps. The point is, here you can see some regions, right? Here or where was the famous one? I think it's surprisingly not actually the longest stretch of conserved things. You can see that there are conserved regions, and the hypothesis at least should be that these are important for the function, whereas some other parts, maybe here, it seems less important to have exactly the right amino acids. And if you take any pair of the sequences, you still get a kind of the same picture, but it's not as clear. The signal for having this very strongly preserved region here is much stronger if you have more sequences. That's all I want to say here as motivation. The biological uses of this are manifold. One is to take sequences where you already know they have a similar function, and then you can zoom in where exactly is the interesting thing in the sequence happening. You can also take sequences where you know they should be similar, but maybe there's variation. We didn't talk about eukaryotic genes, so let me skip that detour. You can use it for various things. You can also try to take for proteins where you know that they are highly conserved. You can take the similarities that you find to build kind of a relation, a weighted relationship. Here you see that the sequences are actually grouped so that the more similar sequences are closer together. And so it found out that human and mice are closer, whereas chicken is already a bit further apart, and then there's a jump to zebrafish and these frogs. For us, what changes from the previous part in this chapter is we have K sequences instead of just 2, again over some alphabet. They may be of different length. We'll, for the analysis, often assume they're the same length just to keep notation simple, but you can definitely deal with whatever lengths. An alignment, now it used to be columns, two letters in a column where you could have a gap symbol. Now there's K of these. So I'm taking the alphabet, add this gap character. That's my sigma minus or sigma gap. And I'm taking columns of K of these symbols. And then a sequence of these columns, that's an alignment. Right? So in this picture, any of these 5 tuples here, that would be not very nicely drawn. That would be one of these entries. And then the alignment is just a string of these columns. The other thing that changes is we need a score. We need a way to decide how good a certain column is. And there's actually many options. We've already seen this in a restricted form in the last chapter where we talked about motifs. There's this picture from. They also align sequences on top of each other, and we said we have to somehow assign a score for how well this alignment is. The difference with motifs, there it was this promoter region in front of a gene, where remember maybe the the video with these angry-looking blocks that you can't pass. No RNA polymerase for me. Here, it's really known that they're preserved in exactly the right length. There might be single replacements of nucleic acid bases, but there's no insertions or deletions possible really in these motifs. For the general multiple sequence alignments, full as before, you can stretch things by adding these gap symbols. So you could take the score that we've used in Unit 2, the total Hamming distance, which as a recap, you kind of find a consensus string by doing a majority vote in each column, and then you count how many rows are different from the consensus. Here we'll do something different, which maybe a bit better reflects the scores if you have gaps in there, and if you expect that maybe the sequences are not really very equal. Here for the motifs, the idea was there should be extremely conserved parts. Here we're a bit more relaxed. So what we'll use is called the SP score, the sum of pairs score. That's where the SP comes from. So it's, again, you sum up the scores of all the columns, and the score of one column with these K letters is just summing up all pairs in that column of all possible row pairs, and then using any pairwise alignment score. So the main benefit of this SP score is you can use whatever fancy pairwise alignment score you've worked out to be useful, and you could lift it to a multiple sequence alignment. Okay? So again, the total score for one alignment, you would have to sum this over all the columns. That's the same as before. It was always additive. Let's first look at how we can compute those in the same way, generalizing what we've done so far. This is one picture from the book where they illustrate again the 2D version, pairwise alignment. And I just want to stress, you can think of it as finding a shortest path from topmost to bottommost, but the edges have labels, have weights. In particular, for edit distance, the diagonal ones where there's a match, like this red one here, has a weight of 0, therefore free. Whereas a diagonal edge like this one, where it's A and C, has a cost 1, and same for the vertical and horizontal edges. But with these edge costs, you can think of this as being finding a shortest path in this directed acyclic graph. If you look at more than 2 sequences, you can do the very same thing. It just now becomes a k-dimensional graph. So instead of this rectangle, it becomes cuboid or whatever k-dimensional thing you want to draw there. For 3, I can still draw it, I guess. Maybe it looks like this. And then you would, I don't know, start up here, end up here, and you have to somehow make your way through there. That's fine. So the same kind of dynamic programming approach works. Now, if you go higher and higher in the dimension, at each point you can go in the same, stay in that dimension in the same, or go one step back. But you can do this in all combinations. So you have 2 to the k different combinations. Minus the one where you don't do anything. So here we had 3 options, which is 2 to the 2 minus 1. With 3 sequences, we already have 7 options, 2 to the 3 minus 1. And this blows up exponentially, clearly. Another way to say the same thing, if you count the number of vertices in this graph that we're trying to find shortest paths in, that number is roughly n to the k if the strings have length n and we have k strings. So you can do this for a few sequences, maybe a handful is fine, but quickly explodes. So that seems like we can't do this. And maybe not so surprising if you think back to what happened with the motive finding problem. This is an NP-hard problem in the general case. So specifically this, okay, the general version proven in this paper is whatever edit distance score you take, whatever pairwise sequence score S that you take, as long as it's a metric, and whatever alphabet size you have, as long as it's 2 letters, then the problem to find the best possible alignment where the number of strings is part of the input and the thing you optimize is the SP score, that is an NP-hard problem. Maybe I can morally sketch the reduction briefly, but I'll refer you to the paper if you want to see the calculations. I think the reduction itself is cute enough, but the calculations get messy, I think. The reduction is from vertex cover on cubic graphs. So cubic just means 3 regular, so every vertex has exactly 3 edges. So we're taking input for this problem, a graph of this sort, and a number. And the question is, can we find a vertex cover, right? Let's say C. And this is supposed to be a cubic graph. So 3 regular. Okay. Now we're constructing some strings and some thresholds, and we'll actually use edit distance. So the distance we choose is edit distance. Then the SP score is the sums of edit distances. We can use sigma is 2. I'll only show this for the special case. Okay, so maybe this doesn't belong into the proof. Here I'm pretending that I'm only looking at the special case, and you can show the same construction also works in more general, but the calculation becomes even nastier. We'll construct 3 kinds of strings. One are strings that are a 1 for every vertex. And then there's lots of zeros in between. And the exact number you have to work out, but it's the same number between each pair of 1s. I'll just copy this. It roughly matches. Maybe it doesn't quite work. So these are template strings, and we will not have a single one of these, but many, many copies. So B copies of these. Then we'll also do another thing. So this is 1, 1 for each vertex. V1, V2, and so on. Then we also have B copies of a string that forces us to select a subset of vertices of size C. And this is a string that has just C1s, okay? But in any good alignment, you'll have to put these in alignment with some 1 columns, because again, you have many copies of these. The copies of these first string, they will all be aligned with each other. Anything else just drives up the cost by so much. If you make B big enough, it'll be above the threshold. Same for these. All of these B copies have to be aligned to the same vertices. Anything else, the cost already blows up too much. So these select columns of vertices. And now you have to add for each edge in in the graph. Oh, yeah, undirected, right? Let's just write it like this. For each undirected edge in the graph, you now have a string that, again, it looks a bit more like this first one. But it only has ones for the two vertices that this edge connects. So you may have one that has 0 here. I'll copy this whole thing. Maybe it's cleaner. So these are all zeros, except for, say, these two, which are ones. But now I'm going to shift this thing around a bit. There's going to be extra zeros at the beginning and at the end. Only cheating a slight bit. And between them, I'm going to delete a bunch of zeros. Roughly the same. So this means unless I want to pay at both ends for all these zeros, I'll have to shift this one inward. Oops. In any good alignment, this will rather look like this. Because if I leave this sticking out at the end, it's going to be too expensive to match those zeros, to replace this with gaps in all the other strings. So I'll have to align it so that only as much sticks out left and right as needed, which means I can only put one of the ones in agreement with some of these picking vector ones. And you do this for every edge. And then you can maybe see that you can pick a threshold so that if there's a vertex cover, every edge can be aligned so that at least one of the two ones is in agreement with all these B copies. Again, think of B as close to infinity. Very, very big, polynomially big. If you can at least bring one of the ones in agreement with one of these picked vertices, then you're not paying as much. If you have any edge where you cannot pick either of the two ones to align with one of the pick vertices, you'll pay this cost of all the pairwise distances with this column will pay extra, and that signals there's no vertex cover. So let's call this is T strings, this is P strings, these are edge strings. And then the game becomes counting exactly what the SP score of this alignment is, showing that any other alignment can only be worse, and showing that you can separate the yes and no cases. And it's a bit messy, so I'll spare us the details. Now, we still want these multiple alignments. If it's NP hard, what can we do? Someone should do a lecture on this. One option is you give up optimality. And that's something where the SP scores are fairly well suited for. First observation is if you have the SP score of some K sequences, A1 up to AK, you can always upper bound it by producing some alignment, right? That's pick some alignment that you construct in some way. I'll show you more in a second. That's an upper bound for the distance you get from the optimal alignment. And you can also lower bound this sum of pairs alignment by taking the actual pairwise distance, ignoring the rest. So I'll have notation for this on the next slide. Whenever you have a multiple alignment, you can just focus on 2 rows, forget about the rest. That is a valid alignment of these 2 strings. And it will have some score evaluated with the pairwise score. It may not be the optimal alignment if you just focus on these 2 strings, because you were constrained by matching all the other strings at the same time. But it is some score. So whatever you do here, the sum of scores here sums up the same. It's the same sum, right? But here I'm taking a different score. It's the score of this alignment where I only look at the ith and jth row. And this may not be the optimal. Okay, the notation will use M for this, sorry. This is a bit Python-like syntax. If you think about this, taking all columns, but then picking out rows I and j. What it's supposed to mean is if you have a specific multiple alignment, in particular one that gives you the best SP score, you can take out the rows that correspond to strings I and j and take their score. That score is lower bounded by the optimal alignment of these 2 strings in isolation if you forget the rest of the other strings. That's why for this sum of pair scores, you get an upper bound from any alignment and a lower bound from the best pairwise alignment. And so there's some hope that you can approximate this and use this in a branch and bound algorithm for finding shortest paths. Again, remember this k-dimensional edit distance graph. If you somehow have a way to prune off entire branches of the graph, then you're in good shape. And that's a standard approach if you have a lower bound for the distance for some node to the target. And that is worse than what you know for some other vertex as the entire distance, then you can skip even looking at that vertex. And for that, we need precisely some lower and upper bounds for our true distance that we can quickly compute. So the last thing I want to show you is that we can indeed get an efficient approximation for this SP score. And that's useful in isolation, but you can in particular also use it as a building block for this branch and bound algorithm, which is still going to be an exponential time in the worst case, but oftentimes substantially faster than this n to the k. Okay. If you think about how you could potentially approximate multiple alignments, you somehow, I don't know, maybe there's other ideas, but one intuitive idea is that you somehow add 1 string at a time and hope for the best. Somehow treat this as an incremental problem, add 1 more string each step. That's at least something worth trying. And sometimes it works. For example, here are 3 strings. They're not at all chosen specifically to illustrate a point. One has A's and then T's, then this has T's and then G's, and this has A's and then G's. Along these edges, there's the optimal pairwise alignment, where here you want to bring the A's into alignment, here the T's and here the G's. And it turns out here you can combine these pairwise alignments in a smooth way into this multiple sequence alignment. And you keep all the matched pairs in the multiple alignment. Now, this does not always work if you take this last string and reverse it, right? Then this alignment here now wants to align the middle G's. This alignment wants to align the A's behind the G's, and this wants to align the T's before the G's. So in a way, we've created a cycle. Right, here we would want A, then T, then G. But here we want the T's, then the G's, then the A's, and here we want the other direction. So that's not gonna nicely go together. in a way you can say these pairwise alignments are incompatible. There's no way to just glue them together and still get a valid alignment. They split up strings in an incompatible way. Tough luck. So what can we do? The thing that goes wrong here is precisely that we looked at things in a cycle, and if you don't do that, everything's fine. In particular, you can think of arranging your sequences in some tree. So for 3, you could have done just a path. And in general, you can do a path, but it works for any tree. Then you can compute the best pairwise alignment along all of the edges. And then you can show whatever alignment you have between A1 and A2. Let's do some concrete example to make this a bit more concrete. And maybe it's a good idea to just use this bad example here. So we have to decide on an order. Instead of going all the 3 edges, let's delete arbitrarily one of them, say this one. Then whatever order we pick, say we first take these 2. So we start with this A, T, 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 and then 4 gaps. So this was, say, A1, this was A2, and now we've cleared this edge. We kind of contracted this edge, right, by building the alignment. And now we add in A3. And so we have an alignment with A2. I should probably write down, let's not be confusing more than necessary. Let's say this is A1, this is A2. Now I'm trying to add A3. I have an alignment with A2, which is right here. Now we'll need to make some room, right? The alignment I have with A3 and A2 would say I have AAAT, I have 4 gaps, and then I'm putting my string A3 below here. Now, for making this a complete alignment, there's things left here, right? Sorry, yeah, missing these 4. There are some other columns that are gaps in A2 that didn't exist in our alignment for A2 and A3. That's these 4. For these, we just add another round of gaps in A3, and we still retain a valid alignment. And what's more, as long as we decide to treat the alignment of 2 gaps as 0, this didn't occur in a pairwise alignment, but in the multiple alignment, it can happen that there's the first string sticking out with more G's, but the pairwise alignment between A2 and A3, if I just zoom in on these 2 now, there's these gap columns, and we just treat them as a 0. That's my convention, but it also is a sensible convention. Then the statement is, whenever I do this procedure with a tree, then the score of the alignment that is induced by this multiple alignment for, say, A2 and A3 is the same as this optimal score that I started with. Because all I did to make it fit was adding alignment columns where both are 0. So I'm adding 0, right? Now, unfortunately, this does not mean that the resulting multiple alignment as a multiple alignment is optimal. Because there could have been some better way of grouping things. And maybe there's no way of building a tree to give us the best alignment. All of these things are possible. But at least we have an algorithm to compute a multiple sequence alignment that starts from optimal pairwise alignments, and we can still choose what tree we want to pick. For the quick analysis that will come, a bit of notation to make things concrete. Capital M will be the multiple alignment. So think of this as this matrix of letters or gap symbols. Again, formally, it's a sequence of columns, and each column consists of k letters from this blown up alphabet, the actual alphabet, and the gap symbol. DSP is the sum of pair scores, and that's something to evaluate a multiple alignment, and it depends on the pairwise alignment score that we'll use. All of this, you can just replace S with edit distance, but the ideas and algorithms are more general. DS, I think I've used it consistently like this before, but that's the score of the optimal pairwise alignment between two sequences. Whereas S itself was a function that gives you the score of columns or the score of some alignment, and you just give the alignment, and it may or may not be the best alignment. Whereas DS, D for distance, should give you the score of the best alignment. And then here's what I mentioned earlier. If you have some multiple alignment, you can just take 2 of the rows and ignore the rest. That is a valid alignment for AI and AJ if you ignore these double gapped columns. And the score of these 2 rows will never be better than the optimal alignment, but at least it's some alignment. Okay? Now, to turn this into an algorithm, we need to pick a tree. And what's the maybe simplest possible tree? A star. Maybe you should have said a path, but for the analysis, it's a star. So there's some sequence that we put in the middle, A, C for center, and all the others are just around that one, connected with some edge. The algorithm starts by computing all pairwise distances because we use them anyways in the next step. So for every I and j, we compute the optimal edit distance, say. Then we find one of the sequences by essentially trying them all off one after the other. We compute what is the sum of the distances from that sequence to all the others. That's the sum, and there will be one that is best. Let that be our center of the star. That's in a way the closest sequence to the others. And then we can construct our multiple alignment following the previous algorithm by essentially merging in one leaf of the star at a time. I think the algorithm is fairly simple. All you're doing is compare pairwise alignments. This merging in really consists of just ignoring columns where there were additional gaps that didn't exist in your alignment. Right? This is all that happens. It's very simple. But how good is this? It turns out it's a 2 approximation, or at least it's actually a slightly bit better when k is small. You can show it's 2 minus 2 over k. Let me sketch at least how do you get this. And probably good to keep the notation somewhere visible. There's one assumption here, and that's also kind of a hint for the proof if you want. We need our pairwise distance that we base this on to be a metric. And I'm sure you're all eagerly working on the next assignment or finish, where you'll show that unless you do stupid things, global alignment distances tend to be metrics. So this is not a strong requirement. all the sensible ones fulfill this. In particular, edit distance is a valid metric. And then we'll show the following. So we have some optimal alignment, multiple sequence alignment. And we have the thing that our algorithm computes, the center star approximation. Let's call it alignment. And to make things, to make the calculations nicer, instead of sum of pairs, I'm doing sum of ordered pairs. What do I mean by that? We said this SP distance corresponds to summing ordered pairs. And let's use V to say I'm summing, well, you can write it I comma J, I guess, all the distances. So here, what do I want? It's the score of the multiple alignment zoomed into I and J. Let's just say in general these are for the two sums. Yeah, no, let's leave it. And same here. Not erase, select. V is a bit nicer to calculate, but really, if you're summing over all ordered pairs, then you're just summing things twice. And the entries where I and J are the same, they'll contribute 0 because they have distance 0. Okay, so whatever you do, V of M is going to be 2 times the sum of pairs distance of the same alignment. In particular, for an approximation guarantee where we take the ratio of MC divided by the cost for optimum, that ratio is the same whether I multiply both things by 2. Right? So that doesn't make a difference. Okay. First step is let's get a lower bound for the optimum. So V of M star, that's again, it's the double sum I and J, the score of the alignment I get when I zoom in on rows I and J. Now this is some pairwise alignment of rows I and J. That's going to be never better than doing the pairwise alignment, ignoring what the multiple alignment says. That's going to be a lower bound for opt. Right? Okay, this is 2 times opt. Easy. Then the second step will be to show an upper bound for our algorithm, the cost for this MC. And we'll basically show that it's, let's call this, what can we call this? Let's call it little m. I think that's still free. We'll claim that this is essentially this approximation 2 minus 2 over k times this m. And then the result immediately follows from that by taking the ratio. So why would that be the case? What we get in the center star alignment, well, first of all, same double sum, right? That should be a star. MC, I'm taking my column I and J. Now we'll have to go back to the observation that I've mentioned here in the drawing. We didn't formally prove it. I mentioned it while pointing to this picture. When you build an alignment from a tree like this, whenever you look at the pairs that you had an edge for, their pairwise alignment is optimal. The pairwise alignment induced by the multiple sequence alignment only has some 0 columns added. Otherwise, its score is the same, and because they're 0, its score is the same as the optimal alignment. So that's kind of fact from above. For all I, the score, if I take in my center star alignment a column C and this J, the score of that thing is the actual best possible sequence alignment of the center sequence and AJ. Okay? That's that. Now, the second thing is our distance is a metric. And that also means it's a metric on these pairwise alignments. So let's draw the star again. If you look at these summands, there's two types of summands. There's ones where one of the I or j is the C, so I'm summing across one of the edges. And then there's the other ones where you're summing over two two leaves. Say these two. Now we would be interested in the edit distance between those two in the direct way. And this we don't know. But what we do know is that taking the detour via C no. That's never going to make it shorter, right? So for all the summands, I have two options. I'm either summing over an edge or I'm summing over one of these. Then I can upper bound it by summing over the two edges. So how often do we sum over each edge? We sum once for I equal the leaf, j equals the center. I guess another time for I equals the center and j equals the leaf. And then for every other leaf, we sum it once. We sum it twice because it's both pairs. Okay. So that sum is indeed every edge occurs exactly 2 times k minus 1 times. There's k sequences in total, which means k minus 2 leaves, and I'm summing it twice for every other vertex. It's actually it doesn't make a difference if it's the center or another leaf. I made life more complicated. So we're summing over every edge 2k minus 1 times. And then what we sum are the edges from I to the edge here. No, that's a round one. Ci. And that one is upper bounded, or is actually equal by the fact to the true distance. So we have to compare M, which is summing all of these guys, to this thing. I think I should have expressed this also in terms of the sum of the distance to the centers. Let's redefine the little m as this guy. And this is supposed to be k times that sum. And that's because we chose the center to be the one where this sum is minimized. So I can pick any, I can hold any j constant and sum over all the others. I'm picking one of the j's as my potential center. Then what remains of the sum is summing up the distances to all the other things. I'm summing up all the distances, holding one fixed, the distances to all the other elements. And the center is the one where this sum is minimal. So if you sum over all the other things, that's never smaller than k times the minimum. You have k such sums. So you can upper bound this one as k times our small m. Then it matches with almost, the scaling was wrong. This one, and then if you divide, you take the ratio, you get the approximation ratio. Okay. Yeah, this step is important because that is the only place where we use that the center is actually the best center that we could have chosen. Other than that, all we needed was the triangle inequality and a bit of rewriting. Okay, sorry for the overtime, but at least the proof is complete now. So we can approximate these SP scores for multiple sequence alignments with a factor 2. If that's not good enough, you can use this approximation to bootstrap a branch and bound algorithm to get the precise answer. And the running time is, in the worst case, still exponential, but in practice, oftentimes, this approximation helps you to prune large parts of the graph. And then you get the optimal answer in less than this n to the k time. Cool, good. That's enough for today, I guess.